Hi guys, my name is Mohammed. I'm going to tell you simple things about injecting comments to detect JavaScript code injection attacks. Abstract: most web programs are vulnerable to cross-site scripting, XSS, that can be exploited by injecting JavaScript code. Unfortunately, injected JavaScript code is difficult to distinguish from the legitimate code at the client side. Given that, server-side detection of injected JavaScript code can be a layer of defense. Existing server-side approaches rely on identifying legitimate script code, and an attacker can circumvent the technique by injecting legitimate JavaScript code. Moreover, these approaches assume that no JavaScript code is downloaded from third-party websites. To address these limitations, we develop a server-side approach that distinguishes injected JavaScript code from legitimate JavaScript code. Our approach is based on the concept of injecting comment statements containing random tokens and features of legitimate JavaScript code. When a response page is generated, JavaScript code without or incorrect comment is considered as injected code. Moreover, the valid comments are checked for duplicity. Any presence of duplicate comments or a mismatch between expected code features and actually observed features represents JavaScript code as injected. We implement a prototype tool that automatically injects JavaScript comments and deploy injected JavaScript code detector as a server-side filter. We evaluate our approach with 3 JSP programs. The evaluation results indicate that our approach detects a wide range of code injection attacks. Keywords: comment injection, JavaScript code injection. Introduction: cross-site scripting, XSS, is one of the worst vulnerabilities in web-based programs. XSS vulnerabilities are exploited by injecting HTML contents or JavaScript code. However, the most notorious effect can be achieved by injecting JavaScript code that gets executed by browsers. The injected JavaScript code can access sensitive information present in web pages and transfer it to third-party websites. Recent research has shown that injected JavaScript code is the primary source of different exploitations such as cross-site request forgery and phishing. Thus, detection of injected JavaScript code is an essential step towards mitigating XSS vulnerability exploitations. A number of mitigation techniques, example static analysis, testing, and scanning, are widely used before program deployments to detect injected code. However, the number of reported JavaScript code injection exploits in released programs is increasing day by day. This indicates that development of vulnerability-free programs is still far from reality. Given that, development of a complementary runtime detection of injected JavaScript code exploitations for web-based environment is important. Currently, browsers enforce the same original policy, SOP, that prohibits accessing the document object model, DOM, of web pages downloaded from one domain to the DOM of web pages downloaded from different domains. However, this protection is not enough to stop the execution of injected JavaScript code. For example, a web page downloaded from might include a script as script src equals http://www.badwebsite.com/x.js/script. The script, x.js, is downloaded from and the code gets executed at the browser side in the context of thus. Server side might be the first place to look for symptoms of injected JavaScript code and mitigate the XSS vulnerability exploitations early. Existing server-side approaches that detect injected JavaScript code suffer from a number of limitations. First, detection of injected JavaScript code is performed at browsers where the server side gathers information on legitimate JavaScript code and transfers it to the client side. As a result, browser implementations need to be modified to interpret the information sent by the server side and execute JavaScript code accordingly. We believe that browser modification is an error-prone task and brings maintenance issues. Second, some approaches detect benign or legitimate JavaScript code present in program implementations and match them against JavaScript code present in response pages. This idea may not detect injected JavaScript code if it is similar to benign script. For example, an attacker might choose to inject a method call that is already present in a response page to introduce subtle unwanted behavior. Finally, most of the approaches assume that websites do not include JavaScript code from third-party websites. In practice, a program might include JavaScript files from third-party websites to have enhanced client-side functionalities. However, an attacker might access to these files and introduce unwanted side effects such as overriding method definitions. In this paper, we address these issues by developing a server-side JavaScript code injection detection approach. We pre- and post-pend each legitimate JavaScript code block with comment statements that include identical random token. We identify the expected features of a JavaScript code block, example method call, method definition, save the features in policies, and embed the policy information into comments. During the deployment phase, we perform a number of checks to detect injection attacks. These include 1. Code without comment, 2. Code with correct and duplicate comment, and 3. Code with correct and non-duplicate comment. However, the actual code features are not matching with the intended features specified in a policy. We apply the proposed approach for server-side programs implemented in Java Server Pages, JSP. We develop a prototype tool in Java to inject JavaScript comments and generate policies based on legitimate code features. We deploy the injected code detector as a server-side filter. We evaluate our approach with 3 real-world JSP programs. Our evaluation indicates that the proposed approach can mitigate many types of injected JavaScript code that might contain arbitrary and legitimate method call injection, and method definition overriding. The results show that the approach suffers from 0 false negative rates. Our proposed approach has several advantages. First, no information needs to be sent to the browsers, and no modification of browser or server script engine is required. Second, a program suffering from weak client or server-side input validation can be safe against JavaScript code injection attacks. Finally, our approach does not require executing actual JavaScript code. Rather, it detects injected code and nullifies any potential damages of website users early. This paper is organized as follows. Section 2 provides an example of code injection attack. Section 3 discusses related works. Section 4 presents JavaScript comment injection followed by attack detection approach. Section V provides implementation and evaluation details. Finally, Section 6 concludes this paper and discusses future works. 2 JavaScript code injection attack examples. In a method call injection attack, an attacker invokes a method that is defined by a user, or supported by native, example array, or host, example document, objects. An attacker might inject a method definition followed by a call to perform malicious activities. In a method definition overriding attack, an attacker modifies the definition of an already implemented method that is provided by a programmer or supported by native or host objects 19, 20. If method definitions are injected without calls, then the attacker relies on method calls that are present in the implemented code. We provide an example of XSS vulnerability in a JSP program as shown in Figure 1, adopted from JAuction, an online auction engine. The program displays the profile of an existing user. Lines 1 to 8 contain JavaScript code that defines two methods, banUser and ActivateUser. An admin can set the status of an auction user as banned and inactive with these two implemented methods. Line 10 extracts a user ID, request.getParameter, ID, and line 11 performs a database query to retrieve the user profile, user method.getUserDetails. Lines 12 to 20 display the retrieved profile of a user related to the ID in a table. We note that the first name and current status of a user are retrieved at lines 14, ars.getStraying, first_name, and 16, ars.getStraying, status, respectively. The table generates two hyperlinks whose href attributes invoke the defined methods. Note that the first_name field is not filtered, example replacing with hashtag and LT before including its value in a response page. Thus, the code is vulnerable to code injection attacks. Let us assume that an attacker injects an arbitrary method call such as script alert, XSS/script. The response becomes td input type equals text name equals first_name value equals script alert, XSS/script/td. When a browser interprets the response, an alert box would appear with the text XSS. An attacker might toggle the behavior of the two methods, banUser and ActivateUser, and inject the payload as script function banUser, document.form.status.value equals active, function ActivateUser, document.form.status.value equals banned/SSIRI. Note that in the injected script code, the two defined methods have similar names to the legitimate code implemented by a programmer. However, the banUser method sets the status field value as active, and ActivateUser method sets the status field value as banned. Thus, legitimate method definitions have been overridden by injected code. Note that the attack does not require injecting any method calls as necessary calls, i.e., banUser and ActivateUser, are already present in the implementation. 1 script 2. Function banUser, 3 document.form.status.value equals banned, 4. 5. Function ActivateUser, 6 document.form.status.value equals active, 7. 8. /script 9. %10. String UID equals string request.getParameter UID 11. Result set ars equals user methods.getUserDetails UID %. 12 table 13. TRTD first name /TD 14. TD input type equals text name equals first_name value equals % equals ars.getStraying first_name %/TD 15. TD user status /TD/TR 16. TRTD input type equals text name equals status value equals % equals ars.getStraying status %17. A href equals JavaScript banUser /A18. A href equals JavaScript ActivateUser /A19 /TD. 20/TR Figure 1. Code snippet vulnerable to JavaScript code injection attacks. In practice, many web-based programs generate response pages where JavaScript methods are defined before they are invoked. However, between method definition and method invocation, these pages also render unsanitized user-supplied contents. 3 related works table I provides a summary comparison of related works compared to our approach based on 5 features: modification of JavaScript code, detection of legitimate method call injection, method definition overriding, and injected JavaScript code downloaded from remote website, and usage of JavaScript code features. Table I summary of JavaScript injection detection works script code mod. Method call injection method def. Overriding injected code in remote website script code feature Gundi etal24 no yes no Naji etal21 yes no Jim etal8 no Johns etal15 yes no Wersinger etal17 yes no Bisht etal23 no Piet Trazek etal25 no yes no Futuransky etal22 no yes no Chin etal12 no yes no this work no yes Gundi et al. Randomize XML namespace prefix in generated HTML pages at the server side. They annotate HTML tags and attributes with random tokens and send specific rendering policies from the server side to the client side. The policies specify rules for allowing or disallowing rendering of HTML elements at browsers. Naji etal detect XSS attacks through the notion of document structure integrity, where attacker injected code cannot alter the parse tree of DOM. Jim etal generate hashes for legitimate JavaScript code at the server side and send them to browsers to get validated by browsers. Detect reflected XSS attacks based on the observation that injected code is present in HTTP requests and responses. Wersinger etal encode all legitimate JavaScript function calls as syntactically invalid code so that attacker injected code gets executed. Phished etal compare the parse tree of benign JavaScript code with runtime generated JavaScript code to detect attacks. However, the parse tree of programmer implemented legitimate method call and an injected legitimate method call would be identical. Thus, the approach could be circumvented for specific code injection attacks that our approach can address. Some approaches apply tainted data flow-based analysis by marking inputs as tainted, propagating taint information during program operations, and checking operations where tainted data is used. However, propagation of tainted information requires re-implementation of APIs and script interpreters. For injected JavaScript code detection, we mark the boundary of legitimate JavaScript code present in each source files by injecting comment statements before and after the code block. For a given legitimate code block, the comment statements include identical random tokens and the features of the legitimate JavaScript code, example method definitions, and calls. These features should be present in generated response pages. We store features in policies and embed the policy information in comment statements for runtime checking. When a response page is generated, we intercept the page and perform a number of checks to detect attacker-injected code. We first check if any JavaScript code without comment is present or not. If no comment is present, then it is identified as injected code, and the code is removed from response page. If code has comments, then the module checks the validity of random tokens and policy information present within comments. If a token is invalid, then the code is considered as injected. Otherwise, the module checks whether the suspected JavaScript code features match with the features specified in the policy information of comment. If a mismatch is identified, then the code is injected. Finally, the module checks the presence of duplicate comments to detect attacker-injected comments. If injected JavaScript code is detected in a response page, then it is removed along with injected comments before forwarding response pages to browsers. We discuss more on comment injection and policy generation in subsections A and B, respectively. A comment injection: we consider some of the most common cases where JavaScript code might be present. Inline script/script 2. Script inclusion using local source file. Example script src equals a.js/script. 3. Script inclusion using remote source file. Example script src equals/script. 4. Event handler code. Example onClick equals foo and v. URL attribute values. Example of ref equals JavaScript window.history.goback. Table 2 shows examples of JavaScript comment injection for these 5 cases. In the first example, an inline script code defines a method named foo. We pre and post pend the definition with comment statements /t1/. Here, t1 is a random token, example a sequence of 32 random characters. The second example shows that JavaScript code is loaded from a local resource file named a.js. We do not instrument comments for this case as the local JavaScript files are analyzed separately. This allows us avoiding injection of multiple comments. The third example shows a remote JavaScript source file inclusion. We pre and post pend script tags with the comments. This approach is taken as we assume that we cannot modify the remote script file. The fourth example shows an event handler method call named foo. Here, we insert a comment for the method call. The last example shows a JavaScript code present in an anchor tag attribute, ref, value and corresponding comment injection. Table 2. Examples of JavaScript comment injection type: example code with injected comment inline script function foo /script /t1 /function foo /t1 /script inclusion local script src equals a.js script src equals a.js script inclusion remote script src equals script /t1 /script src equals /a.js /script /t1 /script event handler input onClick equals foo /input onClick equals /t1 /foo /t1 /URL attribute value of ref equals JavaScript window.history.goback of ref equals /t1 JavaScript window.history.goback /t1 b. JavaScript code feature-based policy generation. We now discuss some of the most useful features that we extract from legitimate code, followed by the generation of policies in the next 2 subsections. 1. Feature identification. An injected code might not be meaningful unless method calls are present. Similar conclusion can be drawn for injected method definition that might override the behavior or programmer implemented method. Thus, we extract the signature of method definition and call as the most interesting features from legitimate JavaScript code. We identify method names, parameters, and arguments by leveraging a JavaScript parser. Example, Rhino. Table 3 shows 3 examples of legitimate method definitions: user-defined, named and anonymous, host-object method overriding, and 2 examples of legitimate method calls: simple, nested. Table 3. Example features of method definitions and calls along with the number of parameter and their names. The third example shows a host object method, document.write, definition overriding. Here, the expected feature includes document.write as the defined method, 1, parameter count, and arg1, argument. The fourth example shows a simple method call that takes 2 arguments. We identify the expected features as foo, 2, 2, 3. The last example shows a nested method call and the corresponding expected features, foo, 2, 2, foo, 2, 2, 3. 2. Policy generation. The extracted code features are stored in policy files so that JavaScript code present in response pages can be compared against these known features to detect injected JavaScript code. We store the feature information in XML format. Moreover, comments include the policy information. Table 4 shows example code, policy information, and modified comments with policy information in the first, second, and third columns, respectively. Example code: example policy modified comment script function foo, x, y. /script policy ID 1 /policy ID type def /type name foo /name param count 2 /param count param x /param param y /param script /t1:1 function foo x y /t1:1 /script. Input on click equals foo 2 3 /policy ID 2 /policy ID type call /type name foo /name arg count 2 /arg count arg 2 /arg arg 3 /arg. Input on click equals /t1:2 /foo 2 3 /t1:2 Table 4. Examples of policy generation type: example code, expected feature, user-defined method, named, function foo, x, y, foo, 2, x, y, user-defined method, anonymous, var foo equals function, x, y, foo, 2, x, y, host object method, override, document.write equals function, arg1, document.write 1, arg1 simple method call foo 2, 3, foo 2, 2, 3 nested method call foo 2, foo 2, 3, foo 2, 2, foo 2, 2, 3. The second column shows code snippets for these examples, and the third column shows expected features. In the first example, a user-defined method named foo has 2 parameters, x, y. We denote the expected feature as foo 2, x, y. Here, the first and second entities indicate the method name and parameter count, respectively. The remaining entities are the parameter names. The second row shows an anonymous method, i.e., a function without a given name. In this case, the method definition is saved in a variable named foo. This would allow a programmer to invoke the anonymous method with foo. We identify the name of the immediate variable where the method definition is assigned. The first example shows a method definition foo with 2 parameters named x and y. We encode the expected feature information with 4 mandatory fields: policy ID, a unique policy ID, feature type, def for method definition, name, the name of the defined method, and param count, the number of parameters. Depending on the number of parameters, the param field contains the parameter name. The third column shows the modified comment that contains both random token and the policy ID, i.e., /t1:1/. Similarly, an example policy is shown for the method call foo in the second example. Here, the field type is set as call and the arg count saves the number of supplied arguments. The arg saves the arguments. V implementation and evaluation. We implement a prototype tool in Java that parses source files with Jericho 13 and injects comments in JavaScript code blocks present. To insert comments, we modify appropriate program locations. Example event handler method call embedded with comments. The output document object allows us to save the modified program back to a source file. The Rhino 11 is used to parse the JavaScript code and extract the features based on the abstract syntax tree. The random token is generated before inserting comments. We store the generated policies in web program containers. The JavaScript code feature comparator module is implemented as a server-side filter. The filter intercepts all the generated responses to detect injected JavaScript code. We evaluate our approach with 3 open-source JSP programs chosen randomly from the source forge.net. Table V shows the summary of the JavaScript code that is present in these programs: inline, script source inclusion, local, script source inclusion, remote, event handler, and URL attribute value. Most of the JavaScript code is present as inline code or event handler attribute value. These programs employ very few number of local JavaScript source file inclusion. However, none of the programs include remote JavaScript file source. Table 6 shows a summary of the JavaScript code features and the number of policy generated for these programs. The code features include the number of method definition, parameter count, method call, argument count, user-defined method call, and host object method call. Table V summary of JavaScript code types: program name, inline, script inclusion, local, script inclusion, remote, event handler, URL attribute, JVote 22020, JAuction 211011 JInsure 15201321. Table 6 summary of features and policy generation. Program name, method definition, param count, method call, arg count, user method call, host method call, total policy, JVote 6 17 13 17 11 2 14 JAuction 45 82 84 81 81 3 44 JInsure 26 38 36 2 13 23 52. The number of policy generated for these programs vary mainly due to the way method definitions and calls are present in these programs. For example, multiple method definition and calls are present in just one code block. Example inline. Thus, we get less number of policies. Example JAuction. However, JInsure and JAuction have the highest number of calls present in event handler and URL attribute value. A experimental setup and evaluation results: we deploy the modified programs, injected comments, in a Jakarta Tomcat server, version 7.0, running on Windows 7. All programs store information in the MySQL database. Our evaluation is a two-step process. First, we execute programs to inject JavaScript code while performing functionalities that accept inputs and store the injected code, denoted as initial functionalities. Second, we execute programs to perform functionalities so that injected inputs are retrieved from storages and appear in response pages, denote as complementary functionalities. In particular, we observe whether the responses contain injected attack payloads or not while enabling the filter. Table 7 shows the number of initial functionalities, brief description of initial and complementary functionalities. We choose 1, F1, 4, F2, F5, and 3, F6, F8 functionalities from JVote, JAuction, and JInsure, respectively. Table 7. Summary of functionality program FN initial complementary JVote F1 create poll view poll JAuction F2 F3 F4 F5 add user, add top level category, add first level category, add auction view profile, view top level category, view first level category, view auction list JInsure F6 F7 F8 user registration, agent registration, add policy update user profile, update agent profile, view policy. We apply 8 types of JavaScript code injection attack during our evaluation. Table 8 shows a summary of these attacks, denoted as a 1A. The first 4 attacks, a 1A4, inject no injection of comments. However, the remaining attacks include injection of incorrect, a 5 and a 6, and correct, a 7 and 8, comments. Moreover, the attacks include injection of arbitrary, a 1 and a 2, and legitimate, code injection that is present in programs, a 3 and 8. The code injection includes both method call, a 1, a 3, a 5, and a 7, and method definition overriding, a 2, a 4, a 6, and a 8. Table 9 shows a summary of the injected JavaScript code, columns 3 to 10, for the 3 programs. We observe that in the JVote program, only one host object method call is present, confirm, in the response page related to F1. The method generates a dialog box to take consent for performing specific actions. Thus, we are able to generate all the 8 types of attack cases, a 1A8. For the JAuction program, the response page of viewing profile, F2, contains 2 method definitions and calls. This allows us to apply all test cases, a 1A8. However, the response pages for the remaining functionalities, F3 F5, contain no legitimate JavaScript method call or definition. Thus, we are able to inject only a 1 and a 2 attack test cases. In JInsure, multiple method definitions, example check all and check null, are present in response pages related to complementary functionalities, F6 F8. This allows us to apply all the injected attack types, a 1A8. The last 2 columns show the total number of injected attacks and total number of detected attacks, respectively. We observe that our approach detects all the injected test cases for all the programs. The obtained false negative rate is 0, which is computed as 1. Hashtag of detected attacks / hashtag of injected attacks. Table 8. Summary of attack types. Attack brief. Attack description. 1. Inject a method call dissimilar to legitimate method call, no comment. A 2. Inject a method definition in a call dissimilar to a legitimate method call, no comment. A 3. Inject a method call similar to a legitimate method call, no comment. A 4. Override a method definition, no comment. A 5. Inject a method call similar to a legitimate method call, incorrect comment. A 6. Override a method definition, incorrect comment. A 7. Inject a method call similar to a legitimate method call, correct comment. A 8. Override a method definition, correct comment. Table 9. Summary of injected attacks and detection rates. Program FN A1 A2 A3 A4 A5 A6 A7 A8 in JDET vote F111111111188 J auction F2 1111111188 F31100000022 F41100000022 F51100000022 J ensure F61111111188 F71111111188 F81111111188 Conclusions and future work. XSS vulnerabilities could be leveraged to perform malicious activities by injecting JavaScript method calls and method definition overriding. Existing server-side JavaScript code injection detection approaches can be eluded by injecting legitimate JavaScript code or altering code downloaded from trusted websites. This paper addresses these challenges by injecting comments for legitimate JavaScript code that encode legitimate code features in terms of method definition and call signatures. This approach makes it very difficult to inject arbitrary and legitimate JavaScript code. During response page generation, we perform a number of checks to detect injected JavaScript code. The approach detects a wide range of attacks including arbitrary and legitimate method call injection and overriding legitimate method definition. We implement a prototype tool to inject comments in JavaScript code. Our evaluation results on 3 real-world JSP programs show that the proposed references 1H. Shahriar and M. Zulkernine, Mitigation of Program Security Vulnerabilities, Approaches and Challenges. Table 9. Eluded by injecting legitimate JavaScript code or altering code downloaded from addresses these challenges by injecting comments for legitimate JavaScript code that encode legitimate code features in terms of method definition and call signatures. This approach makes it very difficult to inject arbitrary and legitimate JavaScript code. During response page generation, we perform a number proposed references 1H. Shahriar and M. Zulkernine, Mitigation of Program Security Vulnerabilities, Approaches and Challenges, ACM Computing Surveys, to appear. 2H. Shahriar and M. Zulkernine, Taxonomy and Classification of Automatic Monitoring of Program Security Vulnerability Exploitations, Journal of Systems and Software, Elsevier, Volume 84, Issue 2, February 2005 JavaScript Security 11 Rhino, accessed from http://12e. Chin and D. Wagner, efficient character level taint tracking for Java, Secure Web Services, November 2009, pages 3 to 11. 13 Jericho HTML parse 1415 M. Johns, B. Engelman, and J. Posga, XSSDS, server-side detection of cross-site scripting attacks, PROC of the ACSAC, California, December 2008, pages 335 to 344. 16 Cross-site scripting, 17 P. Wersinger, C. Platzer, C. Ludl, E. Krita, and C. Krukel, Swap, Mitigating XSS Attacks Using a Reverse Proxy, PROC of the SES, Vancouver, May 2009, pages 33 to 39. 18 H. Shahriar and M. Zulkernine, Mutech, Mutation-based testing of cross-site scripting, PROC of the 5th ICSE Workshop SES, Vancouver, Canada, May 2009, pages 47 to 53. 19S Paula and G. Fidon, Subverting Ajax, PROC of the 23rd CCC Conference, Berlin, December 2006. 20 B. Hoffman and B. Sullivan, Ajax Security, Addison Wesley. 21 Y. Nagy, P. Saxena, and D. Song, Document Structure Integrity, a robust basis for cross-site scripting defense, PROC of the NDSS, San Diego, California, February 2009. 22 A. Futuransky, Idiotism, and A. Waspian, a dynamic technique for enhancing the security and privacy of web applications, PROC of Black Hat USA, Las Vegas, 2007. 23 P. Phishing v. Venkat Krishnan, XSS Guard, Precise Dynamic Prevention of Cross-Site Scripting Attacks, PROCTH suffers from zero false negative rates. Due to the limitation of the JavaScript parser, some tasks require pre-processing of JavaScript, such as removal of comment tags and removal of return keyword in event handlers. Future work includes finding automated ways to perform these tasks. We also plan to evaluate runtime overhead of our approach.